Okay, so this is the third video in my Yocto Linux video series. And in the last two, we created a basic Linux system and brought up the ZedBoard. And then in video number 2, we installed the QEMU system emulator for the ZedBoard. And this video is going to introduce the idea of doing some Linux kernel module development. Now, the topic of building kernel modules is well outside the scope of what we're going to do in this video. There are plenty of references on the internet for how to create a kernel module. I'm going to go through like a dumb one today, just a hello world example, with the idea being I want to show how to use the tools and get them integrated into that system emulator and then even onto the ZedBoard. The actual process you're going to follow is kind of beyond this scope. So to get started, what we need to do is to make sure that our computer system, by the way, this first round we're going to do it on the PC. We're going to develop a kernel module for the Intel PC, in this case my virtual machine. I like to do it just to make sure that I have some sanity around the module that I'm building, just so that I know where I'm at and what I'm after, because when you're doing with embedded hardware, it's one more variable, and so the development tools may or may not be adequate to being able to tell you where the errors are, and you may have a valid module but you have a misconfiguration in a tool somewhere and then you don't know what the problem is. So I always try to start on the PC, and to do that we need to make sure that we have the software for it. So first of all, I'm going to get out of the pokey Yocto directory, and I'm going to make my own here. And I'm going to make a little hello world module, and since I'm building for the PC now, I can use regular Ubuntu tools, and so I'm going to start off by installing the kernel module or the kernel header files that will allow me to compile code against that kernel. So this is kind of a standard command, the apt-get command to install software. The package is Linux headers, and I need the version specific for the kernel that I'm building on, which is this current version. The uname-r gives me that kernel revision, and so the backticks run the uname command, capture the output of it, and replace it on the command line. So when this thing runs, it's going to automatically create a command line that says apt-get install Linux headers 4.8-36-generic, and I've already got them installed. The next thing we're going to do is go into our hello directory, and we're going to do what's called an out-of-tree module build. I'm not trying to make a module that's in the Linux kernel source code. I'm not trying to change the Linux kernel source code in any way, shape, or form. I'm going to use it to build my module. And to do this, I'm going to make a makefile. And the makefile is going to be a little special. It's going to actually use the kernel module itself. Oops. The kernel's makefile itself. So here we see I need to list, on this first line, I'm going to list the object files that the kernel module is going to be compiled with. So if I have multiple files, I would list them across here. I'm only going to have one stupid file. But that's going to be part of the objects for this module. The kernel version is, again, we're going to be using that uname command to get the kernel version. And so whatever I do a make, it's going to do the right one for the current kernel that I'm using. Okay, and then the next piece of this is the first target is the make all, and that's kind of the default. And a make all is going to use the make file that's loaded in lib modules at the current kernel version build directory. And the m equals pwd is another shell variable. This is the current working directory. And this is telling the Linux make system that I want to build modules in this current directory. If I were to try to do a make clean, that works fine. If I try to do a make all or just a make, it's looking for hello.o and it can't find it. So then it looks for hello.c, and it can't find that either, and so it fails. Well, and that's kind of what we expected. So the next bit of this is going to involve writing the actual C source code. And although it's C language, it's just a little bit different than what we would normally do when we're writing C code for Linux. So the first three .h files are, well, first of all, the first thing to note is our include files now aren't using the standard ones from user include. They're using ones for the Linux kernel. The first one provides all of the module definitions that I need to be a module. The second one has the basic core functions that you'll find in the kernel. And then init is actually going to have what it takes to initialize a module. And we'll see what that looks like here in just 1 second. So this first function is hello start. There's nothing special about that name. We could have called it Bob. The important part here is that the function signature looks like a static int and then the name of the function and no arguments. The other really vital thing is that it has this tag, this underscore init. This is used by the module compiler to the C compiler to mark this as the initialization function for this module, so that when we load this module, this is the function that gets called, kind of like what you'd have when you run a program and it calls main. If we have a program that is invoked when it starts, we're going to have another one that gets invoked when it ends. So this function is just going to be the cleanup for the kernel module. Whenever the kernel module is being unloaded, this C code gets called. And then the last thing we need to do is just kind of mark one more time here what our initialization and exit functions are going to be. So if that's all done now, I should be able to do my make command, and oh, look at that, I have no syntax errors. That's a kind of a fluke. And what we wind up with is this this KO file. This is a kernel object file. If I do an ls, I see that I have this KO file in my directory. And to load it, I could either copy that kernel object file into the kernel modules for my operating system, and that would be the lib modules directory that we used in the make file. Or I can just use this utility called insmod. And insmod will insert a module into the list of runtime modules. Before I do that, I just want to show how many different modules are in my system to begin with. This is pretty typical of a modern Linux system to have just a whole pile of dynamically loaded kernel modules. If I were to now insmod my hello KO file, I can't do it as a regular user. That makes sense. You don't want your users just being able to arbitrarily modify the kernel. But if I sudo that command, and now I do my lsmod, I can see that there's my lsmod, or there's my hello module. It's using 16K of memory. That's pretty much the smallest it can be. And it is loaded with no problem. The 0 means that it's not being used by any other module. To see the output from that print K, I guess I should have paid some more attention to that. Let's take a look at this file one more time. Instead of doing a print F, which prints to a file, we did print K, which prints to the kernel log buff. And note that this is really important, that kern info is not followed by a comma. Kern info is the log level that this message is going to be displayed. So this is an informational message rather than, say, kern error or kern debug. And when you have these different log levels system-wide, you can turn on or turn off whether or not you want info messages to be recorded. To see these messages, I actually have to look at the Kernel Log Console, and that would be through the dmesg command, dmesg. Do it again. And we see here, for instance, that there's my hello, I'm here to help message. And so we see that it loaded. We also see some messages from loading the kernel module in the first place. We see loading out of tree module taints kernel, and the module license is unspecified. This is actually kind of one of the things I don't like about Linux kernel modules, because what it's really saying here is you don't have a copyleft license. Yes, copyleft, not copyright. It's a Unix or a Free Software Foundation thing. We don't have a specific license that says we can use this and distribute this. It's not technically open source. And so the Linux kernel is built to object to loading anything that's not open source, which means technically our Linux kernel is now tainted. It has non-open source software in it. That's what the message means. If I try to remove this module, again, I can't do it unless I'm root. If I do my sudo and I do my dmesg, we see our goodbye message now in the dmesg log. And if I do my lsmod and grep for hello, we'll see that it's not there. So at this point, we actually have a working kernel module. It doesn't do a whole heck of a lot, but it's there and it works. So we could further extend this module, but that's not really what I want to do. What I want to do next is take this module and move it over into the Pokey Linux, into Yocto. So I'm going to go into Pokey, and to do the next couple of steps, I need to use a few commands from the Yocto Linux command set. And remember, when we first started everything off with Yocto, we talked about modifying a configuration file, and we actually ended up adding the Xilinx, meta Xilinx layer and the open embedded layer. Well, I need to make my own layer, and I know where we're going. I'm going to go ahead and I'm going to create this layer, Yocto layer, create, and you give it a name. I know I'm ultimately going to the 7-segment display. And so I'm going to go ahead and create this new layer as my layer. I'm just going to take the defaults here. And what it's done for me is it's created a meta 7-seg directory. And if I go into the meta 7-segment directory, it's populated it with just a basic kind of configuration. And in particular is this conf file that has the layer conf. And the layer conf says look through all of the directories and look for a directory that contains, that starts with the word recipes, and then look for a bb append file and then just automatically append them. bb append is the bitbake command. So what we really want to be able to do is populate this directory here, the Pokey meta 7-seg directory, with a subdirectory called recipes-something that has another directory followed by a directory that contains a bb append file. Yikes. Well, the good people at Yocto have made this a little bit easier. In this meta skeleton directory are skeleton recipes for everything you might want to be able to do. And so what I'm going to do is I'm going to cp-rp. Cp is the Unix command for copy, -r is recursive, and p is with permissions. And we're going to do I guess I don't really need the permission, I just do it force of habit. cp-rp meta skeleton recipes kernel, and inside here is their own hello mod, and I'm going to copy that. Well, actually I want to copy the whole recipes kernel directory right here. We'll do it that way. That gets me the right directory structure. And if I cd into recipes kernel now, I see that I have Linux, which is actually going to do a custom compile of Linux, and I don't want to do that. So I'm just going to get rid of that directory. rm-rf will forcibly remove everything in that directory. And what I'm left with now is a hello mod, and this hello mod is got a slightly different structure than what we looked at before. It has one more subdirectory than what I did for my PC. But if I cat the hello world C, it's basically the same thing. And look, there's the missing module license. So this guy won't even taint my kernel. That's always kind of good. The make file here, a little bit different than what we did before, but basically the same elements. We still see the make, but make has been substituted with the a shell variable. The kernel source has been substituted with a shell variable, and the module directory has been substituted with another shell variable. The reason for that is that when Yocto's build system, the bitbake command runs, it's going to fill these in with whatever it's building for that target system. So I think we're all good. We're ready to go. And so what I want to do is I'm going to go ahead and open up another terminal window, and I'm going to go to my build system. Okay, so in the previous video when we built the emulator, we set an environment variable for machine equals QEMU Zynq 7, and then we did our bitbake, and I could choose to do the core image minimum. Oops, almost forgot. I need to go into the build directory and I need to add the new layer that we just created. So to do that, I'm going to edit the conf file, and there's our BB layers conf file, and I'm going to put my new layer at the end of that list. And now I can do my machine equals QEMU Zynq 7 and bitbake, and I could actually ask for just that one kernel module. Oops. I need to make sure that I have the open and embedded variables in my path, so I do the OE init build end, and now I can go ahead and do that. And we'll actually be able to watch Yocto parse all the recipes, and it should find my hello mod recipe and build that module for the emulator. Okay, so it only took a few seconds, and now I can do run QEMU Zynq 7. Let this boot up. Log in, and let's see if so even though it built the module, it didn't actually build the actual, or didn't include it in the file system. To get it into the file system, we have a few choices. I don't have SFTP, I don't have FTP, because this is a very minimal system, but I do have TFTP. Oh, remember TFTP is a server and client process that is kind of insecure, but for the right task and for the right circumstances is a handy way of being able to deploy small files back and forth between a host and its embedded system board. To begin setting this up, I'm just going to go ahead and sudo apt-get install tftp d. No, tftp hpa. think. It's been a little while since I've done this. So I believe at this point I have my TFTP service started. The default. So files are going to go into varlib tftp boot. Okay, so here I am in my Yocto Linux. We're going to go to our build directory, and if I navigate through here into temp, there it is. It's just called hello.ko, not hello. Oh, that makes sense. The recipe was called hello mod with a dash, but the actual file is called hello. Well, then maybe it is on here. Let's just take a look. Nope, not there, but I want it to be. So what I'm going to do is I'm going to cp temp sys. I'll just copy this. cp this file. You know, actually, I don't even want to cp this file. Whenever this file changes, I want the TFTP file to change. So I'm going to go here to varlib tftp boot. This is a really cool Unix trick. And I'm going to do a link. I'm going to link to Yocto build temp sysroots. Oh, jeez. I can't type. QEMU and lib modules. So I'm going to create a symbolic link. A link. Actually, I don't even need to do that. I can just do a link. I can link the hello.ko file to this directory, but I've got to do it as root. And so now this hello.ko file is available from TFTP boot. And the other thing I'm going to need to know is what my host machine is. It looks like it's going to be 192.168.7.1. And I know that because that's my gateway. So if I do TFTP, okay. So TFTP, this is ridiculous. It transferred the file from my virtual machine into the virtual machine running inside my virtual machine. But the virtual ARM system now has this file, and if I do an insmod on hello.ko, hey, look at that. Hello world. And if I do an RM mod on hello.ko, it's gone. Let's go back. I just want to hammer away at how this process works. If I go back to my meta 7seg directory and I go into my recipes kernel and I go into my hello mod and I go into files just going to change the string. So we're not really changing the functionality, we're just changing that string. I'm going to save it. And I'm going to rebuild it. So that's going to rebuild the .ko file, but that .ko file was linked. So if I look back here at my TFTP server, oh, it's showing me the time and date of the link. Well, let's see if it's the different file. Let's see if it works. So we'll do our TFTP command again, and we'll do our insmod. I didn't clean. So this time we see 481 tasks, of which 480 didn't need to be rerun. And oh, let's see. There's a unit command that I like to use called strings. And strings will show you all of the text strings that are in a program. And it doesn't look like it recompiled. So we're going to have to try to force this thing to recompile here. Dope! I fell into a trap for new players, I guess. When I made the link, I forgot that in Unix, if you have a link to a file and you delete the original, then the link gets severed. So then I had two different files. So we had properly updated the file, I just didn't actually catch the link. So what I did is I removed the original link that we did with the ln command, and then I did it again as an ln-s command to make a symbolic link. And so now if I do an ls-l in the file, we see that hello.ko is like a pointer. It points to the real file. And now if I do my strings command, we can see here that my string is actually hello world test test test. And so now if I do my TFTP in the simulator, oh geez. Well, now it doesn't have permission to access the file. So that's kind of a bummer. We'll just copy it. There, now it's there, and so now insmod hello.ko, and look, there it is, and then rmmod hello.ko. This was painful, but there are important steps that we followed because you need to make sure that you know the kind of these sanity tests to make sure that you can move the kernel around, kernel module around, and that everything is working. For the last stupid little trick, I want to see if this works on my ZedBoard. Okay, so I brought up realterm, and if you remember, the IP address I had to use in the simulator was a fake one, a 192.168. That address is never routable. That's just used for internal purposes. One problem I'm going to have is that my virtual machine is sitting behind my behind a NAT firewall. So for example, if I do an ifconfig on my regular machine, it also has a fake 192.168 IP address. So the first thing I'm going to have to do to be able to access that TFTP server from the ZedBoard is to change my settings on my virtual machine and make my network adapter bridged. Bridged means this virtual machine connects directly to the physical network. If you were to look at the physical machine and kind of watch the traffic that's going to come out of it, in a bridged environment you'll see two different Ethernet addresses, one for the host machine and now one for the guest machine, the virtual machine. So when I do this now, we're going to see Linux over here is going to have a fit. It says, oh no, you've disconnected your Ethernet, and oh no, now you've reconnected your Ethernet. And if I do another ifconfig command, we can see now my IP address has changed to 157.160 something. That means I'm connected to Shippensburg's network. And so if I go back to real term and look at real term now, let's see how to log in. I can do my tftp-g-r hello.ko, and the file name that I need to get it from now, or from the host name that I need to get it from, is 157.160.39.139. So the ZedBoard doesn't have an IP address, and to get one, we're going to do the udhcpc command. This is the DHCP client built into the ZedBoard. And if I do an ifconfig on it, now it has a 157.160 IP address. Should be good to go here. So now TFTP worked. I have my hello.ko file. Hey, it worked. And now I can do my rm mod hello.ko file. That felt so good, we'll do it again just to make sure it will all work. That's a lot of things connected, but this is kind of the bulk of the process. And in fact, we're almost over the worst of it. This is allowing me to move files over this kind of insecure TFTP server. It's a very primitive way to share files. You would definitely not want this on a public-facing IP address. It's just not, there's like no user authentication or anything like that. But for this kind of specialized embedded development, it's kind of the way to go. I've seen some shops where they'll actually set up a little mini router on somebody's desk, on an engineer's desk, and then they'll have two Ethernet cards in the machine, and they'll bind the virtual machine to both the local area network and to the that kind of unique little router, and then their little embedded board will plug into that little router. Or we could even do the same thing with like a USB Ethernet USB to Ethernet adapter, and then use that to plug into the embedded hardware. There's a number of different strategies to kind of keep these things locked down, and as we evolve, we'll kind of go through a couple of those. But at least for now, we have the ZedBoard talking to the virtual machine. We can move a kernel module from source code into a compiled image for our target or for our simulator, and we can test it out. Now you can actually start developing kernel modules for the ZedBoard. We will pick that up and kind of use that to develop the 7-segment display in video number 4. Thanks for watching.